overcome the loss that I already discussed in starting, that 54 billion per year annual loss. Due to these developments, apps, we overcome the loss annual year and overcome the securities issues. Thank you. If there is any question.
Hello.
Thank you very much, Baba. Is there any question from the audience? So, Fawwa, can you please go back to your literature review slide?
Yes, ma'am.
I would like to see your base paper.
G?
What is your base paper?
Base paper, I didn't add the references in these, and the base paper achieved the 95 to 97 accuracy, but my paper word base accuracy achieved is 97%. Paper is in camera ready versions, and okay, requirement is only 10 to 11 slides.
Where did you get your data set from?
Kaggle.
And it was one data set or more than one?
One data set and
ham, spam and
label. We only worked on 2 to 3 columns, ham, spam and smishing, and label is, it is
okay,
0, 1, 2.
What was the size of the data set?
10, 191.
Thank you.
Thank
you. So much.
Thank you, Ms. Farwa Khalid, for sharing your valuable research insights with us. Next, I would like to invite Adnan Beg to present paper ID 224, titled as Optimizing 3D Object Detection with Radar Camera Fusion Using a Single Backbone Approach. Sir, please come on the stage.
Assalamu alaikum. My name is Adnan Beg, and I am a PhD scholar currently doing my PhD from University of Sultan Zainul Abidin, Malaysia. And currently I'm working as a senior lecturer at University of Management and Technology. And it's honor to present in IEEE conference. The topic of my presentation is optimizing 3D object detection with LiDAR camera fusion. Okay. So what is 3D object detection? 3D object detection is a fundamental component of autonomous driving system. It enables vehicle to perceive and understand their surrounding environment in 3 dimensions. The system identifies and localizes the objects such as vehicles, pedestrians, and other road objects that is captured by using LiDAR and different visual cameras. Autonomous vehicles rely on multiple sensors for perception. There are 2 sensors that we are using. First one is LiDAR technology, and second one is cameras. What LiDAR technology actually do? Provides accurate depth and spatial geometry, and camera provide rich visual and texture information. Basically, LiDAR is a sensor that will reflect the light to measure the distance from the object. And while we use camera for the visual capture of that object, like object color and its texture, etc. Main motivation of this research is autonomous driving needs accurate object detection. In previous research, it will work very less accuracy in a moderate and difficult environment. LiDAR and camera both have a limitation as well. In previous research, someone used LiDAR and someone used cameras, but obviously individually there has a limitation, and existing fusion methods are slow and complex. Need a fast and efficient solution. So what's the exactly problem? That is problem statement. Yes. So existing method use separate networks that will use dual backbone for LiDAR and cameras. So by using dual backbone approach, they use two different networks to process separately for the camera and for the LiDAR technology data. So obviously that will increase the processing power as well, and also increase the memory size as well. So LiDAR data is sparse and irregular. Camera data lacks depth information. So that's why we are using both the sensor to capture data. Need a solution that is efficient, accurate, suitable for the real-time environment. Research gap. Most existing methods are dual backbone network, as I earlier explained you. This leads to high computational cost and increased memory usage. Many fusion methods are, please, next slide. Many fusion methods are complex and inefficient, limited focus on real-time performance. Need a simple and efficient and unified architecture that will reduce the processing power and also will reduce our memory cost. So, proposed solution. Propose a LiDAR camera fusion LCF 3D framework. Use early fusion to combine data from the both sensor. Because as I explained earlier, that in a previous research, they are using dual technology to handle the data, and basically there are three steps, that is input, processing and output. So it will combine the data after processing. So in our technology, we use earlier fusion framework that will capture the data in the start during the input, that will combine the data. Like data, for example, I would say that if we have two information from the two different sensor, one is from the camera, second is from the LiDAR. So LiDAR give us the distance, for example, the distance is 10 centimeter, and the camera gives us visual aspects, that is like car color is red. So in an early fusion, that will assign that car color is red with 10 meter distance. So that will reduce our processing cost as well. Secondly, introduce us, that is a single backbone architecture obviously, and perform point-wise feature fusion. Use RGB plus in enhanced, that is RGBD and RGBI. So with RGB images, that would also have RGB distance information plus its intensity information. That will reduce the computation cost, model complexity, and improve accuracy and real-time performance in a dense area. So that is the methodology as shown in the figure. We are capturing data from the two different sensors. One is from the visual camera and other is from the LiDAR. So it detects the RGB images from the camera, and LiDAR points clouds from the LiDAR laser beam, and then project to the image plane that will associate that visual with that fusion points. And then point-wise feature fusion will be extracted by a CNN, and then feature fusion will be applied, and then we will apply a voxel grid, and after that 3D detection head, our final object will be detected. So that is the flow that I have already explained. So that is the result. As you can see in the graph, that earlier research will consume 19,500 Mbps data and 9.5 FPS per second, frame per second. And now in our research, we will reduce our memory cost and our speed efficiency. So our performance is 4,500 Mbps that will utilize the memory and 20.8 FPS as well. So, conclusion, propose the LiDAR camera fusion framework, LCF 3D, use single backbone architecture, obviously that will reduce our processing power and our memory cost, applied point-wise feature fusion for better integration, improved detection accuracy on a kitty dataset, that is a simple trained dataset we took from the Kaggle, and achieve better performance in moderate and hard scenarios. Earlier research was work efficiently in a simple environment, but in our research that its performance is very good in hard scenarios. Maintained real-time efficiency with the low computation cost. So thank you so much. If there is any question, just let me know. Thank you.
Thank you so much, Adnan. Do we have any questions from the audience?
अच्छा मेरा चूँकि फील्ड नहीं है, ठीक है, आपके जो स्टूडेंट से है, मेरा काम साइकोलॉजी और न्यूरो साइंस और इससे रिलेटेड है. मैं अगर जब ये चीज़ देखता हूँ कि ये जो आपने लाइडार का कंसेप्ट है इस चीज़ को, तो दो एस्पेक्ट मैं आपसे समझना चाह रहा हूँ इस बात को. नंबर वन, कि क्या जो ये कंसेप्ट है ये विद इन अ सिस्टम एक लिमिटेड उस डोमेन में काम कर रहा है, जैसे कि वो एक गाड़ी के ऊपर लगा हुआ है और इसके बाद वो जो है उसको फंक्शन कर रहा है और वो वहीं से डिटेक्ट कर रहा है, जैसे कि वो सेल्फ ड्राइविंग कार्स हैं तो वो उसको देखते हुए असेस कर रही है और इसके बाद उसकी की बेसिस पे ऑपरेशनल अपने जो से परफॉर्म कर रही है, ब्रेक सिस्टम कोई भी चीज़ें, ठीक है. एक चीज़ ये तो हो गया विद इन दैट कार लिमिट. और वो दूसरा चीज़ है लेवल के जिसमें कि वो नेटवर्क बेस्ड एनालिसिस जो है आगे की इंफॉर्मेशन लेके वो नेटवर्क बेस्ड है, ठीक है. अच्छा, मैं अब इसी बात को देखता हूँ कि हाउ ह्यूमंस वी एज अ ह्यूमन हम कैसे हमारा जो सा है न्यूरल नेटवर्क कैसे वर्क करता है, ठीक है. हमारे पास इंफॉर्मेशन के जो चैनल्स हैं वो दोनों चैनल्स हैं, सेंसरी चैनल्स हैं, वो इंफॉर्मेशन इन्वायरमेंट का इनपुट मुस्तकिल ले भी रहे, ठीक है, और इसके बाद उसको भी प्रोसेस कर रहे हैं विद रिस्पेक्ट टू एवरीथिंग दैट यू सेड. फॉर एग्जांपल विद रिस्पेक्ट टू कलर्स एंड डेप्थ एनालिसिस, डिस्टेंस एनालिसिस, ये सारी चीज़ें उसके साथ, और उसकी बेसिस पे वो एक इनपुट दे रहे हैं, ठीक है. इसके लिए भी एक वो सेट है, दूसरी तरफ वो सेट है जो फीडबैक मैकेनिज्म है, जो मोटर फंक्शंस है, यानी मोटर फंक्शंस ह्यूमन बीइंग का बिहेवियर्स हैं, और दूसरी तरफ आपका जो सा है इफ़ आई एम नॉट रॉन्ग कि इट्स लाइक योर कार, ऑटोनोमस कार जो आपकी, ठीक है. तो अब ये जो फंक्शंस हैं आप इसमें से आई रेड इट समवेयर कि ये बिल्कुल उसी तरह से उसी फंक्शंस को लिया कि जैसे कि ह्यूमन बॉडी और न्यूरोनल फंक्शंस जो से वर्क करते हैं, क्या हम उसी तरह ही कर रहे हैं या ये बिल्कुल एक डिफरेंट ट्रैक्स है इसके. थैंक यू.
ओके, थैंक यू सो मच फॉर द क्वेश्चन. अच्छा, इसमें मैंने ऑलरेडी बताया कि हम न्यूरल नेटवर्क को ही यूज़ कर रहे हैं. डीप लर्निंग का आर्किटेक्चर है जो कि एट द एंड आपका सारा वो वोटिंग करके आपके रिजल्ट्स जनरेट कर रहा है, और इमेज को जो कैप्चर करता है उसके लिए आपका CNN जो है कन्वोल्यूशन न्यूरल नेटवर्क, वो इमेज के ऊपर प्रोसेसिंग करता है, और उसके बाद डिफरेंट, जिस तरह से आपने बताया कि ऑब्वियसली कि ह्यूमन बीइंग भी इसी तरह से हम ऑब्जेक्ट को डिटेक्ट करते हैं और डिफरेंट कलर्स की बेस पे हम उसको परसीव करते हैं. तो इसी तरह से बिल्कुल आपने ठीक कहा कि ये सारा आपका न्यूरल नेटवर्क के ऊपर ही बेस करता है, उसकी बेस के ऊपर ही प्रोसेसिंग होती है, और इसके अंदर एक एक्स्ट्रा जो चीज़ें हैं दैट इज़ द हार्डवेयर. तो हार्डवेयर ने ऑब्वियसली बात सिग्नल लेना है, डाटा लेना है, और डाटा लेने के बाद प्रोसेसिंग करनी है। इमेज की जो प्रोसेसिंग है वो आपकी CNN कर रहा है, और आपके जो दूसरा फ्यूजन पॉइंट्स को आपको जो है वो फ्यूजन मॉडरेट एक वेरिएबल है वो उसको हैंडल कर रहा है।
अच्छा, तो इस वक्त जो आपका चैलेंज है वो क्या है? स्पीड का चैलेंज है?
इस वक्त हमारा जो चैलेंज है कि देखें कि प्रीवियस रिसर्च के अंदर अगर कोई ऑब्जेक्ट आपकी गाड़ी के आगे जा रहा है, या सम टाइम होता है कि कुछ ऑब्जेक्ट जो है वो प्रॉपर्ली विजिबल होते हैं, कुछ ऑब्जेक्ट जो होते हैं वो हाफ विजिबल होते हैं, हाफ अपीयर होते हैं। लाइक कोई अगर पैदल चल रहा है तो सम टाइम इस तरह से हमें वो ब्लाइंड पॉइंट्स बनते हैं, या सम टाइम ऐसे होता है कि आपके पास जो डाटा आ रहा होता है, डाटा पॉइंट्स आते हैं, वो कोई इतनी डेंस पॉइंट नहीं होते, वो काफ़ी ज़्यादा उसके अंदर डिफरेंस होता है। तो बेसिकली हम उस ऑब्जेक्ट को क्लियरली आइडेंटिफाई करवा रहे हैं, जिसकी बेस के ऊपर हम मैंने आपको बताया था 2 टेक्नोलॉजी यूज़ की हैं। लिडार क्या, एक लेज़र बीम है, वो लेज़र बीम के थ्रू उसके डिस्टेंस को एक्चुअल कैप्चर करेगा कि इस ऑब्जेक्ट के दरमियान इस गाड़ी का क्या डिस्टेंस है। और सेकेंडली हमने जो कैमरा यूज़ किया है वो उसके विजुअल एस्पेक्ट्स की इन्फॉर्मेशन लेगा। इन दोनों चीज़ों को कंबाइन करके फिर हमने इसके डाटा को प्रोसेस करवाया हुआ। कैमरा जो है वो विजुअल, फॉर एग्जांपल गाड़ी का कलर जो है, फॉर एग्जांपल कैमरा क्या करता है, गाड़ी का कलर क्या है, फॉर एग्जांपल गाड़ी का कलर क्या है, हमारे पास रेड कलर है, और जो लिडार ने क्या चीज़ आइडेंटिफाई की कि इसका डिस्टेंस क्या है, फॉर एग्जांपल 10 मीटर है। सो हमारा सिस्टम क्या करेगा, उसको अर्ली फ्यूजन उसके ऊपर अप्लाई करेगा कि रेड कार विद द डिस्टेंस 10 मीटर, तो वो आपको पहले ही उसका सिग्नल आ जाएगा। सो दैट इज़ अ हाइब्रिड नेटवर्क फॉर द लिडार टेक्नोलॉजी एंड द कैमराज, एंड आल्सो वी विल प्रोसेस थ्रू अ डीप लर्निंग न्यूरल नेटवर्क्स। थैंक यू सो मच सर।
Thank you, sir, for your presentation. It's a request kindly for the presenter. Please make sure that कि अपना जो time limit है उसमें in between रहे. Maximum 20 minutes you are allowed. Next, I would like to invite Minahil Kamran to present paper ID 63 titled as Hybrid Ensemble Learning for High Precision DDoS Attack Detection in IoT Networks. Please proceed.
So, Assalamu alaikum everyone. My name is Minahil Kamran and I am currently doing my bachelor's in computer science from University of Central Punjab. And it's a great honor for me to be here today and present my research paper, which is about hybrid ensemble learning for DDoS detection in IoT networks. So let's start off. As we know that IoT networks are rapidly increasing day by day. As the result, the denial of service attacks are also increasing day by day. So the traditional IDS systems that include the Snort IDS or the Cisco Firepower are not able to actually detect the modern and evolving IoT attacks. So what we propose is a hybrid ensemble model that consists of 3 independent models: the extreme gradient boost, the random forest model, and the multi-layer perceptron that is trained on a Kaggle data set, and it's interpretable using SHAP analysis. What we proposed proves out to prove accuracy of nearly 98% with F1 score of less than 1 second of detection, that is near to real-time detection systems. So here raises a question that what are IoT systems and what makes them so vulnerable? IoT systems are basically anything hardware or software that has the ability to communicate over internet through the data. So these systems are vulnerable because the protocols used in them are mostly outdated, or the credentials used are not strong enough to prevent them from the security attacks. So there are many security loopholes in these systems. As apparent from the previous botnet attack that happened in 2016, it was evident that how much loss the DDoS attacks can cause to our critical infrastructure. It can literally cause the terabit scale of damage to our critical infrastructures. So let's talk about the literature review first. So these are few of the papers and the models that we have reviewed first. People have tried to use the machine learning models independently. These machine learning models are good, lightweight, however, these are not robust and they lack accuracy. So we proposed a model that is based on accuracy. Secondly, people have tried to use the deep learning models. Deep learning models are also excellent for studying the nonlinear relationships. However, they are computationally very heavy and complex. Thirdly, features are explained using the old techniques that are the Pearson, ANOVA, or InfoGain methods. However, there is a chance that important features are lost in between them. So we proposed a balanced model of different independent models, and we are using SHAP analysis to analyze all the models. So this is the gap that we have identified, that all the existing systems are not evolving with the evolvement of the IoT attacks. Deep learning models are good, but they are latent. The machine learning models are good, however, they are not robust as the other models are. So we need a balanced approach. So this is the dataset that we are using. It's the IoT dataset 24. It's a synthetic dataset that we have achieved from different sensors that include the cameras and sensors, etc. It's a labeled dataset. It has two major classes. That is the Benin class, that is for the normal attack packets, etc., and the DDoS attack class. And further information about the duration, the protocols are also mentioned in this dataset. So let's talk about the methodology. We have different modules. Our first module is the pre-processing and feature engineering. In this, we will be cleaning the noise in the data. We removed the missing values. We encoded and did the scaling approximately. And then we handled the outliers at 99th percentile. And we removed the closely correlated features that could overfit our model. Next, we have the core, the heart of the system, which is the soft voting ensemble. We're using 3 models. We're calculating the probability by simple soft voting technique. If the probability exceeds the 0.5 limit, then it means that the certain packet is close to attack, so we can detect the IoT attack in it. If it's less than 0.5, then it's safe and it's good to go. And for evaluation matrices, we are using the same accuracy, precision, and recall and F1 scores to validate our results. This is the overall workflow. As you can see that the input data is being processed, and then it is passed to the hyperparameter models, and then it is the soft voting ensemble is choosing one outcome, and then it is going again, as I told, that 0.5, if it's greater than 0.5, then it's going further for the SHAP analysis, as we can see at the last module. So this is the experimental setup. As I've told, that we are using a Kaggle data set. We are doing an 80-20 train test split in 5 rounds of the training. And then evaluation matrices are already discussed, and model compares are random forest, the extreme gradient boost, and the MLP. So as evident from the table the results, the ensemble results are far better than the independent models that have achieved. So we can easily conclude that the ensemble learning technique is better than the independent models, and it has very low false positive ratio. And the ROC graph further confirms that it is categorizing each class more better than all the previously methods used. It is compared with the SNORT IDS and Cisco IDS too. So we're talking about SHAP analysis. SHAP analysis is basically used to tell that why a model did certain prediction. So these are the mean SHAP values, and it has clearly prioritized the features that are directly related to the DDoS attacks in networks. So as we can see that it has our proposed model has high recall. So it means that it is near to real-time detection system. It has very low false positives. It means that it can be implemented in real scenarios. It is better than traditional IDS systems, as I've told that all of them are rule-based and no one is evolving like our model can. And as we can see, that model has proved to be an outclass model using on CPU as well, so we can basically deploy it on cloud or edge environments in future as well. For practical and academic benefits, I would say that I've said that it is practically applicable in real-world environments. Moreover, we have used a model that is basically a combination of multiple machine learning and deep learning models. So it's basically an academic breakthrough to study about more such models. And for future work, I would say that right now we are using doing a supervised learning, and we can extend it to unsupervised forms as well. We can work on multi-classes as well, and we can deploy it on cloud and further systems as well. So I'd like to conclude it by saying that the proposed model is robust, and most importantly, it is practically implicable as well. So at the last, I would like to acknowledge my university, University of Central Punjab, for providing me with the research environment. And I would also appreciate the Bahria University, Lahore, for organizing such an insightful conference. These are the references that led me through this research. And thank you so much, everyone, for listening.
One question, please. There are several ensembling methods like bagging, boosting, and stacking. So why you chose soft voting only?
Our main concern is to decrease the complexity, as already the models that are being used are computationally heavy. So for keeping it less in computation as well, so we are using soft ensemble rather than the other methods. Yeah.
Any question from the audience, please?
Thank you so much.
I would like to appreciate being an undergraduate student. This is enlightening to see you engage in conferences.
Thank you so much.
Kudos to you.
Thank you for your presentation. Next, I would like to invite Muneeb Ahmed Khan to present paper ID 223, titled as Smart Security Framework, a Pose-Aware Multi-Stage Enrollment and Recognition System.
Many face recognition systems fail. Many face recognition systems fail, not because the person is unknown to the system, but because the system has never seen the face in a slightly different pose. Good afternoon, everyone. I am Muneeb Ahmed Khan from University of Management and Technology, a student of 6th semester. And today I am presenting our work, Smart Security Framework, a Pose-Aware Multi-Stage Enrollment and Recognition System, which is a team collaboration effort by our team at UMT Sialkot. To understand why this work matters, let us begin with the motivation behind this work. Face recognition systems such as ArcFace, FaceNet becomes a core component of everyday life. This is widely used in authentication systems, mobile systems, in border security management systems, and even in attendance systems. More deep learning methods such as FaceNet and ArcFace have been widely used and is widely working on improving the recognition accuracy. But one thing remains there, that is, a very little attention is given to the enrollment stage of the process, which is a concerning thing, and our paper is proposed on working on that set of the system. This leads to high false rejection rates and losing trust in biometric systems. So the key question comes here is that instead of only improving the recognition accuracy, can we improve recognition reliability by improving how enrollment data is captured? So this leads us to the problem statement addressed in our work. Traditional recognition models work on single image capture. This comes with a lot of issues, including unstable recognition performances, high rejection rates, reduced trust in biometric systems, and a lot more. So our goal was to reduce all these issues and propose a simple enrollment pipeline that improves recognition accuracy and is user-friendly at the same time. To address this problem, we propose a pose-aware multi-stage enrollment. Our work focuses on improving the enrollment stage rather than modifying the underlying system architecture. This approach makes the system more independent, easy to integrate with whatever the underlying architecture is, and the practical for real-world deployments. Moving on to system architecture. System architecture slides, we have 6 major stages over here, starting with a video acquisition stage, which involves using webcam input. Then we have the face detection and the landmark extraction using facial features. Then comes the most important stage, which is pose validation using geometric variations and constraints. Then comes the embedding generation from the validated poses, and then have the storage. We have used vector database storage. Then comes the last stage, which is the recognition and decision-making stage. We have used the following technologies, including media pipe. We have used for feature landmark detection and extraction, which converts 2D features into 3D for modeling. Then we have used FaceNet embeddings by Google, which has been proposed in 2015. We have used for embedding generation. We have used ChromaDB vector storage, and we have used OpenCV, an open source computer vision library for image processing. All these libraries have been chosen decisively because they were real-time and efficient performance and robust performance. A key component for our system is accurate pose estimation. So, head pose estimation is based on 3 main parameters, starting with the pitch, yaw, and roll. Pitch represents how the head moves upwards and downwards. Then comes the yaw, which represents how the head is tilted and rotated towards the left and right. Then the last one is tilt, which represents how much the head is tilted. These angles are computed using perspective and point formulation applied to landmark feature extraction. For example, we have defined the threshold ranges. For example, the frontal pose is based on pitch, based on yaw, which is less than 28 degrees. And for side turns, we have defined this, the threshold as greater than 22 degrees. Using the validation mechanism, we have made this system. We have defined the enrollment sequence. We have divided the steps into 10 simple steps, starting with the look straight, turn left, turn head to the right, look upwards, look downwards, tilt head to the right, tilt head to the left. Then comes the 2 basic expressions we have used, including smile and a neutral face. And then comes the last one, which is move slightly back. Each steps contribute equally to our system. This reduces the core objective over here was to reduce the false rejection rate and improve the accuracy. This reduces the chance of false rejection rates. Moving on, we then evaluated whether our system worked as expected or not. For this experiment setup, we have used a limited number of participants because 3 number of experiments were to be conducted. 2 enrollment approaches were used, including the baseline approach, which uses a single frontal image, and the second one is our proposed pose-aware multi-stage enrollment framework. Each participant were able to, after the stage we have performed, each participant were able to perform 5 recognition attempts, making it to 50 recognition attempts. This resulted in 50 recognition attempts. We have used the L2 distance over here and FaceNet embeddings to store the embeddings and compare the embeddings with what is stored at the recognition stage, what is stored at the enrollment stage, and what is given at the authentication or the recognition stage. We have used the L2 distance with a threshold of 0.66, which has been defined in earlier researches. The key question we have here was whether this proposed framework actually improves recognition performance or just a hypothesis. Results clearly show single pose-aware frontal image single frontal image makes the accuracy at 76%, while our proposed model makes the accuracy to 96%, with the false rejection rates reduced from 20% to just 2% in our proposed system. This confirms that post-diversity during enrollment may have a significant effect on the overall approaches. Performance improvements come purely from enrollment system. One thing have to be observed over here is that we have not redesigned the recognition pipeline. We have used the same recognition methods being applied overall. We have just redefined the enrollment stage over here. Moving on, we have also analyzed the enrollment stage to check whether the user interaction, whether it is completely up to the mark, whether user will be able to complete it in the time in an easy way or not. So the results also shows that the average time was 54 seconds, starting from the 28 degrees to almost 82 seconds, which is manageable in 1 minute. We have also observed in our experimental setup that some poses had taken more attempts than the usual, which were the basic expressions like smile and the held tilt poses. Despite this, we have a 100% completion rate in the enrollment phase. Moving on to the limitations slide. This work presents a pilot evaluation because early stage experimental studies work on feasibility studies rather than checking how large scale the model is, how large scale it can be applied to. Future work will surely include large scale evaluation, diverse demographic groups, and evaluation under varying lighting conditions. We will also be evaluating its performance in real world deployments. The framework is designed to scale easily as it is dependent on the open source library widely available and widely used. Moving on to the final and conclusion slide. To conclude, we have contributed a post-aware enrollment framework. We have also validated pipelines. We have also reduced the false rejection rate from 20% to 2%, improved accuracy from 78 to 96%. Our future work will include evaluation or large scale, as I told earlier, and then it will be adaptive estimation and real-time deployments. Reliable biometric systems do not just work on strong models, but they also work on how strong the enrollment structure is. Thank you for your time and attention. Now we welcome your questions.
Any question in the audience, please? Okay. Don't you think the participant size, only 10 participants, it's very small size for training?
Yes, we do acknowledge that the limited size of the participants, but as I mentioned earlier stage, we have seen that early stage experimental studies. We have focused on a feasibility study rather than on the large scale evaluation. We're focused to check that whether this system can be is feasible or not, whether it can be scaled later or not. The main purpose of our study was to check the feasibility of our proposed system. I hope I have answered the question.
Many questions. Okay, thank you.
You're welcome, sir.
Thank you, Munib, for your presentation. Next, I would like to invite Sayyid Rizwan Ali to present paper ID 221, titled as A Multi-Layer Smart Computing Architecture for Tectonic Optimizing Using Machine Learning and Evolutionary Algorithms.
Okay, ji, assalamu alaikum. Okay, first of all, I'm sorry about my voice because I had only a 3-hour sleep because I don't know what happened in the night. I couldn't able to sleep. So, First of all, I'll come back to my multi-layers. The framework about the smart computing, it has been designed with the help of the industry for the solution for the technopreneurial about their business models. Because sometimes if you are having a business model, and in that if you are using the machine learning and an AI algorithm in that, and it is very drastic situation if the outcomes is not come according to up to the mark. Because in the business, you have to run it, you have to earn it, and you have to deliver it. So this is a dilemma. So what we have done, we have in the USA, the High Hope company, we had a collaboration with that, and they had a collaboration that you need to make a model and propose a framework, and then that you need to have the 3 frameworks about the consecutive intelligence, which is based on the forecasting about your business processes, and the sensing and evolutionary optimization, which is based on the PSO and other factors. And the last one is about the entrepreneurial. I think the presentation, okay, it's coming over here fine. I don't know, I think it's not showing well over there. So the last one is about the entrepreneurial strategy, which is based on your focus on the businesses, okay? And the next one about the research gap. In that, we have the machine learning and the AI prediction analysis and the evolutionary algorithm, which has been used for the optimization and entrepreneurial strategy for decision making. Because we have seen that we haven't find, maybe there it is, but what we have searched, could not find the undefined framework for that integrates that the domains in a cohesive system, particularly absence for the multi-layer. We have architecture which connects the intelligent data processing with the adaptive optimization and the strategic execution, which limits the effectiveness of the current approaches and the real-world tag applications in entrepreneurship. Okay, so we have just designed in the 3 frameworks over there, and these are the gaps which we have identified, which we have flashed into the slides. Okay, so and afterwards there is the kind of the contribution on the left-hand side. You can see about the integration of the framework, operational construct, and the feasibility artifact. This is the contributions about the census and the optimization, and the third one is the act what you are doing in a practical way, right? So, and then afterwards, we have find the research gap, but we were doing the literature review, which shows that in AI and start computing, when we have the predictive analytics, in that we have found that the dissection, the pattern recognition improves the sensing and uncertainty. The AI supports the decisions and the product design in the digital marketing and learning from the feedback, and the evolutionary optimization, which is the GAPSO, and the ACO are the effective in a large multi-criteria space for the trade-off, and the bio-inspired as well. And an entrepreneurship strategy that we have found that the decision-making, which I have earlier mentioned about in the problem statement of my presentation, that is the main thing about their decisions and the opportunities, the recognitions in the resources for their experimentation. So we have adaptive and the learning based on the optimization, increasingly relevant to the version context. And basically, if you just come in the one line of the research gap is about the previous studies have rarely integrated the prediction, optimization, and the human experimentation, and a one measurable, oh no, just a one fingertip, you will get the answer for the one measurable closed loop architecture, right? So this is the research gap which we have find out of the research, okay? So this architecture is based, which we have discussed in the first slide, that the consecutive about the layer, intelligence layer, evolutionary optimization, which is industrial decisions eligibility, and the entrepreneurial strategy, which we have just based on that, about the marketing science, about the forecasting, about the lead instruction in the cognitive intelligence layer, evolutionary optimization, which is based on the research selections. What are the parameters that you are going to select it, and that how you are constrained with the handling with it, right? And the last one about the strategy means your experimentation, your execution, which is a very important part, that how you are going to interact it, and the learning from the feedback, that what the decisions that you are going to get in the end, right? And then afterwards, we have the operational constructs and the analytics, the core constructs, which have already been discussed about the decisions, eligibility, computational opportunities, recognition, and the resource allocation, operational indicators, a time to decide to upgrade the frequency if it is low at that time, or the signals detection accuracy, especially in the lead time, okay? And the objectives, the value of the improvement for the each segments, and the measurable amount of examples, that the minutes, hours, or per cycles, that how much it will take around is a strategy in like a 1 week or maybe 2 weeks, it depends on the decisions. And after that, the precisions, that the week of the lead time versus the base time, the actual one, right? And the percentage of the total cost reduction with your ROI left means return on investment, that you are investing of it, okay? And integrating AI with the evolutionary computing increase the capacity for the sustainability and the architecture of your innovation in success, right? So in afterwards, when we just go and we found the methodology and the roadmap of the validation, that we have the exploratory synthesis, which we have used ML and AI in this architecture for the technopreneurship, then we have the cross-dependency mapping to identify the overlaps between in it. Then we have module formations for our architecture to testify that. And the last in the validation roadmap to demonstrate about the facilitations. Like we have, you can see in the future empirical extension in the last one, but I'm not showing here, I don't know, it's fine, if you see on that screen, so you can see that clearly about the accelerated portfolio fields in the points, pilots of the incubators, and the multi-case studies using the operational definitions, okay? And then we have the simulations for the proof of concept, which is based on the portfolio of 30 startups that we have took it from in Pakistan and the USA as well. And they are based on the 12 cycles of decisions under demand of their fixing budget with the runway sector, and all allocations efficiency measures on their expected ROI, which is over here, and it's based on the decisions, eligibility, proximity, interface, optimization in a runtime. And we have signals, ALML forecasting, and we have genetic algorithms and the output for their budget allocation, which is the heuristic allocation proportion for the previous life seconds before scars. And then we have final in the experimental results, we have just gone through that their allocation efficiency, the baseline, the 0.1, and our proposed framework is a 1.18, which is, around the 18% of the change. And then the constraint of the violations is about the baseline, the actual one is a 6, okay, you can see over here. And then we have the model is the one which is a less than 83% over there. And decision time, which is the most important and the crucial thing in that about the framework, is about the 0.9%, but we have found this, and our framework is the 1.9, okay, 1.9, which is the 0.5 plus. And then about the portfolio, about the ROI, the return on the investment proxy is a 1, and we have baseline in a 1, and our framework, and we have 1.2, which is the +2%. And this is, you can see the efficiency proxy, we have just shown over here about there, the timeline, and showing that the instructions and then the eligibility over there. And afterwards, the decisions, implementations, and especially the limitations are still left, which we are working on that, and we are trying to improve about the current evidence of the conceptual plus synthetic simulations only. The claims about the real world performance, and is still the empirical evidence is still there, and we need to work on that to make it more accurate and more closer to map your businesses. And the next step to observation data controls, especially in the pilot ways for the multi-sector in a multi-phase. In the last of the conclusion, what we have found out the technopreneurship is in the measurables, which is the guidance of your testable decisions. And what are the major elements of that? The first one is the integrated, your architecture and your optimization construct, feasibility shown, and the research agenda. And thank you. I think my time is over, which is at 20 minutes. Thank you. If any questions, I'm good. And again, thank you very much. And sorry for my voice because I'm not able to speak properly. Thank you.
No questions? Any questions from the audience, please? Thank you.
Thank you, sir, for your presentation. We truly appreciate the presenters for their meaningful contributions and engaging presentation. We will now conclude the morning session. We'll be right back after lunch break and prayer break. Please, presenters and session chairs, you can visit B1 and B2 for lunch at 1 p.m. At 2:20, we will restart our second session. Thank you all.
जी अभी ब्रेक है, अभी 2:20 तक, नमाज, लंच, सारा कुछ.